In this video, we look at the Pauli principle, which is a requirement that multi-electron wave functions must be antisymmetric with respect to exchange of two electrons. Take a system with two electrons, like a helium atom. Its wave function can be written as psi of 1 and 2, where 1 and 2 are shorthands for the coordinates of electron 1 and electron 2. Each electron needs 4 coordinates, 3 spatial ones and 1 for spin. Therefore, there are 8 coordinates total. Now, let's exchange the two electrons. We can write this with an exchange operator. Uppercase P hat 1, 2, operating on psi 1, 2. This exchanges the coordinates of electrons 1 and 2. So we get psi of 2 and 1. Psi 2, 1 is the wave function after the exchange. Now, the two electrons are identical and indistinguishable, so this swap of coordinates should not affect any physical properties of the state described by the wave function. First and foremost, the probability density should be unaffected. That is, magnitude of psi 1, 2 squared should still be equal to the magnitude of psi 2, 1 squared. This is only possible if the exchange adds at most an insignificant phase factor. So, p hat 1, 2 operating on psi 1, 2, which gives psi 2, 1, has to be equal to e to the I phi times psi 1, 2. Otherwise, the probability density would change. Applying the exchange twice in a row, we should therefore get back our original wave function. So p1, 2 squared operating on psi 1, 2 is equal to e to the I phi squared of psi 1, 2, and this should be equal to our original wave function psi 1, 2. So the square of the phase factor, ei phi squared, must be equal to 1. This is only possible if the phase factor itself is either positive 1 or negative 1. So we have either psi 2, 1 equals to positive psi 1, 2, or we have psi 2, 1 equals negative psi 1, 2. The positive sign means that the wave function is symmetric with respect to exchange. And the negative sign means that the wave function is antisymmetric with respect to exchange. So we have two different classes of physically valid wave functions. Now, which one of these two is adequate for electrons? It turns out that many electron wave functions have to be antisymmetric with respect to exchange to be consistent with experiment. This is the famous Pauli principle. It says that a many electron wave function must change sign under exchange of any two electrons. This principle cannot be derived from any other principle, but it is essential for the correct description of quantum phenomena. It is therefore another postulate of quantum theory. The principle is actually more general. Whether the wave function is required to change sign or not depends on the type of particles that are exchanged. Wave functions have to be antisymmetric under exchange of two electrons or protons or neutrons. These particles are called fermions. Wave functions have to be symmetric under the exchange of photons or alpha particles and so on. These particles are called bosons. Interestingly, all fermions have half-integer spin, and all bosons have integer spin. Let's check this principle on a 2-electron wave function. Take the neutral helium atom and put the 2 electrons with spin up into the 1s orbital. The electron configuration for this is 1s alpha squared, or symbolically like this. The 2-electron wave function, psi12, is a product of 1-electron wave functions, lowercase psi1s1, alpha 1, lowercase psi1s2, alpha 2, or in a short form, 1s1, alpha 1, 1s2, alpha 2. With this, we are neglecting the correlation between electrons. Now, let's apply the exchange operator. P hat 1, 2 operating on psi 1, 2 will give us 1s2, alpha 2, 1s1, alpha 1. This resulting wave function is equal to the starting one, so it is symmetric. This is therefore not a physically possible wave function for electrons. From this we see that no 2 electrons in an atom can be in the same orbital with the same spin, or no 2 electrons can have the same set of quantum numbers. This is the famous exclusion principle. It is a direct consequence of the more general Pauli principle. Next, let's look at the wave function for a 1s alpha, 1s beta configuration. 1s alpha, 1s beta, which is written as just as 1s squared. A first attempt at this wave function would be psi12 equals to 1s1 alpha 1 times 1s2 beta 2. Let's exchange the two coordinates. P12 operating on this psi12 is equal to 1s2 alpha 2 times 1s1 beta 1. This wave function is different from the starting one, and it is neither symmetric nor antisymmetric. Again, this is not a physical wave function for an electron. One way to get an antisymmetric wave function is to make a linear combination of product wave functions. In our case, we can use psi 1 and 2 equals 1s1 alpha 1, 1s2 beta 2, that's the wave function from above, minus 1s1 beta 1, 1s2 alpha 2. We can factor out the spatial part, and we get 1s1 times 1s2, and now times the spin part, which is alpha 1 beta 2 minus beta 1 alpha 2. Now, if we exchange the two coordinates 1 and 2, so P12 operating on psi12, we get 1s2, 1s1 times alpha 2 beta 1 minus beta 2 alpha 1. The spatial part didn't change at all, and the spin part changed sign. So overall, we have an antisymmetric wave function. In summary, three things are important. First, when two electron coordinates are exchanged, wave functions can be either symmetric, antisymmetric, or neither. Second, the Pauli principle says that wave functions for electrons must change sign under exchange. They must be antisymmetric to be physical. Third, to obtain wave functions that are antisymmetric and physical for many electrons, we need to linearly combine several products of one electron wave functions, like we've shown here.